So in this video, I'm going to go through the multiple choice for Big Idea 4 from the Princeton Review. So in the first question, it tells you you have a multi-step reaction. And for number 1, it says, what is the overall balanced equation for this reaction? So what you should notice is that you've got A on your reactant side for both step 1 and 2, so that would be 2A. For B, you got it as a reactant in step 1 and a product in step 2, so those are going to cancel. Notice, since you start with B and you finish with B, that is actually a catalyst. If B were formed during the reaction and it were used up, then it would be an intermediate. But in this case, it's a catalyst. So you're not going to have B. So I can immediately get rid of answer A and B. Okay? Then I've got 1 C on my product side for step 1 and 2 C's on my reactant side for step 2 and 3. So that can actually reduce to just 1 C on my reactant side. Then for D, if you notice, D is formed in step 2 but used up in step 3, which means it is an intermediate, which means it's going to cancel out. And so the last thing that's left over is E on my product side. So the answer is going to be D. Right? For step 2, I'm going to use this reaction again, and it says, what is the function of the species B in this reaction? Well, I just said that. B begins, you have it in step 1, and it is not changed by the end in step 3. So as a result, because it exists in the beginning and it exists at the end, it's going to be a catalyst. So the answer is a catalyst, but be careful because it says it is a catalyst which changes the overall order of the reaction. No, the only thing a catalyst does is it lowers the activation energy. So your answer, they tried to trick you with C, be careful. Your answer is D, because a catalyst lowers the overall activation energy for the reaction. Okay? In 3, again, we're going to use this reaction. It says if step 2 is the slow step for the reaction, what is the overall rate law? So my second step is my slow step. So the way that I would write this, I'm going to first write out my rate law. So I'm going to say rate equals K times my concentration of A times my concentration of C. Notice that's an answer. Now notice A is a reactant, it's not an intermediate. C is a reactant in this reaction, it's not an intermediate. So even though step 2 was your slow step, you can keep this as rate equals K times the concentration of A times the concentration of C. So the book tells you that the answer is A because for some reason it doesn't want you to keep C in this rate law. I'm not sure why. I think B is a perfectly fine answer because A and C are not intermediates. However, if we were to treat this problem like C were an intermediate, what we would do, let's assume C is an intermediate, then we would look at step 1 and we would say the rate of A and B being consumed equals the rate of C being consumed because you are in equilibrium. So you would write K times the concentration of A times the concentration of B equals K times your concentration of C. You're going to get C all by itself, and then you can plug in what you got for C in for C. So you would end up getting K times the concentration of A times the concentration of A times the concentration of B, which would give you A squared B. So that's the answer they want for the book. I disagree with it. I think that having rate equals K times the concentration of A times the concentration of C is a correct answer because C is not an intermediate. I would not give you a question on the test that I disagree with. Okay, moral of the story. All right, for number 4, it says, why would increasing the temperature make the reaction rate go up? Okay, so if you increase temperature, that causes the particles to move faster. We know that. If they're moving faster, they're going to collide with each other, number 1, with more energy, and number 2, more frequently. Okay, so which answer matches with that? Well, if you look, B tells you molecules in the reaction will move faster and collide more often. That is the correct answer. Increasing temperature has no effect on your activation energy at all. Your activation energy, the only thing that affects your activation energy is the addition of a catalyst, which would lower the activation energy. But if you increase temperature, your activation energy is the same. What that means is that more particles have that energy to have the reaction occur. So they have enough energy to actually react. So your answer is B. In 5, it tells you you're at 600 Kelvin, and it tells you that this decomposes to form sulfur dioxide and chlorine gas via the above equation. If the reaction is found to be first order overall, which of the following will cause an increase in the half-life of SO2-Cl2? So if you think about it, by increasing your half-life, you're increasing the time it takes for half of that compound to decompose, which means you're slowing down the rate. If you're slowing down the rate, okay, if it's a first-order reaction, rate equals K times the concentration of SO2-Cl2. If you increase the initial concentration, that would increase the rate, which would decrease your half-life because you're increasing your rate. We're wanting to decrease the rate to have a longer half-life. If I increase temperature, again, that's going to increase my rate. That's not what I want. If I decrease the overall pressure in the container, since we don't know the state of matter of SO2-Cl2 for this, I don't know how the pressure would affect it, so it's kind of a weird inclusion for them. And so the answer is D, none of these would increase it. And in fact, A and B would decrease your half-life because those would increase the rate, meaning that the half-life would occur more quickly because your rate has increased. So your answer is D. In 6, it gives you this reaction in this rate law. So we know that the overall order for this is third order, okay? Which means the units for this, remember rate is molar per second. The A times B squared would be molar cubed, which means that my K would need to be molar to the -2 seconds to the -1 in order to get a rate of molar per second. So my answer would be C. For 7, it says the following mechanism is proposed for a reaction. Okay, so I've got a fast, then a slow, then a fast. So that tells me probably I'm going to have to deal with equilibrium. So it says, which of the following is the correct rate law for the complete reaction? So I'm going to first write out the rate law for my slow reaction because that is my rate determining step. So I know it's going to be rate equals K times my concentration of C times my concentration of B. Now, if we look at this, what you should notice, unlike that first problem which I disagreed with them about, B is an intermediate. Since B is an intermediate, that means I cannot leave that in my rate expression. So as a result, I have to look at the reaction above, the fast equilibrium. I'm going to set that and make the rates equal to each other, meaning the rate at which A decomposes and the rate that B decomposes. So what I would write is I would write K times my concentration of A squared equals K times my concentration of B. Okay? Since B is my intermediate, I'm going to get B all by itself, so B equals K times A squared. Remember, the K's all vary. It doesn't matter. It's still going to stay K. And I'm going to plug in A squared, or KA squared, in for B. And what that gives me is that rate equals K times my concentration of A squared, because that's replacing B, times my concentration of C. So the one that matches that is B. In 8, it tells me the reaction above takes place with all of the reactants and products in the gaseous phase. Okay, so I know they're all gases. Which of the following is true of the relative rates of disappearance of the reactants and appearance of the products? So I am comparing rates. As soon as I start to compare rates for different entities in a reaction, I know I'm going to have to use the stoichiometry. Specifically, -1/2 times the rate of NaCl equals 1/2 the rate of NO, which equals the rate of Cl2. Okay, so if that's the case, I know that the rate at which NaCl disappears is going to be equal to the rate at which NO appears. I know that -1/2 of the rate of NaCl, that's going to equal the rate of Cl2. So let's find my answer. So it says NO appears at twice the rate that NaCl disappears. That's false. They appear and disappear at the same rate. So B is going to be your answer. For 9, it tells you when the reaction given above takes place in a sealed isothermal container. The rate law is that, so it's going to be second order overall. If 1 mole of H2 gas is added to the chamber reaction, so I'm increasing the concentration of H2, and the temperature remains constant, which of the following will be true? So if I increase my concentration of H2, I don't change my K. I'm just increasing the concentration of H2. That will cause the rate to increase. So my K stays the same because the only thing that affects your K is temperature. My concentration of H2 increases, which means my rate would have to increase. And so my answer is going to be D. The rate of the reaction will increase and the rate constant will not change. For 10, it gives you a mechanism, and it says, what is the order of the overall reaction? Well, since my slow step is my first step, I know that my rate law is going to be rate equals K times my concentration of NO2 times my concentration of F2. That works, which means that my overall order will be second order. For 11, it says, based on the following experimental data, what is the rate law for the hypothetical reaction given above? All right. So to find the order for B, I want A to stay the same. So I'm going to use experiment 1 and experiment 2. Okay, so from experiment 1 to experiment 2, B doubles while A stays the same. From 1 to 2, my rate also doubles. So remember in your explanations for your free response questions, you would say, when the concentration of B doubles, the rate doubles as well. Therefore, B is going to be first order. Okay, so I got the order for B. For A, I'm going to look at experiment 2 and 3 because that's when B stays the same. So when A goes from the second experiment to the third experiment, it doubles while the rate stays the same. So in my explanation, I would say when the concentration of A doubles, the rate stays the same, therefore it is zero order. So my overall rate law would simply be C, rate equals K times B, because you ignore A since it's zero order and B is first order. For 2, it says, a solution of cobalt ions appears red when viewed under white light. Which of the following statements is true about the solution? So the reason why colors look the way that they are, whatever color that they look, what happens is that a substance will absorb all of the colors from white light, because white light is made up of all of the different colors of the rainbow. The color that is transmitted, that is the color that they appear. So if cobalt ions look red, the reason why they look red is because the only color that they don't absorb is red. So the only answer that matches up with that is D. Okay, so this was a little bit of a weird, wonky question, but just knowing that solutions or anything, the reason why they look the color that they do is because that is the only color that they do not absorb. So grass is green because it does not absorb green. That's the only color it doesn't absorb. So if you put plants under green light, they would die because they can't absorb that light. So just a fun fact. All right, for 13, based on the following experimental data, what is the rate law for the hypothetical reaction? All right, if you notice, I've got 2 experiments where A stays the same, but unfortunately, I don't have any trials where B stays the same. So I can really easily find my order for B, and I'm going to do that right now. I'm going to look at experiment 1 and experiment 2. From 1 to 2, B doubles, and the rate of C also doubles. Therefore, B is first order. Okay? Now I've got to figure out this little tricky part. So what I'm going to do is I'm going to say, all right, from experiment 1 to experiment 3, what happens to A? Well, A doubles. I don't know the order, so I'm going to say 2 raised to the whatever. So in this case, I'm going to say 2 to the n. From 1 to 3, B quadruples, and I'm going to raise that to the 1 because I know that B is first order. From 1 to 3, remember my trick for dealing with the exponents, I'm going to multiply all 3 of those by 10 to the 6th, which means that 2.0 times 10 to the negative 6 becomes 2, 4 times 10 to the negative 6 becomes 4, and then 1.6 times 10 to the negative 5th becomes 16. So 2 to 16, that is increasing by a factor of 8. So based on that, basic math tells me that A has to be first order as well. So your answer is D. Okay? Make sure that you're able to explain this. So in my explanation for determining the order of A, I would say when the concentration of B doubles and the concentration of A quadruples, the rate increases by a factor of 8. Therefore, A must be first order, and that's how I would explain that. Some of you guys are still having trouble explaining. Please don't lose points because you're having trouble explaining. So you say, what happens to the concentration? Does it double, triple, quadruple? What happens to the rate? Does it double, triple, quadruple? And therefore, what is the order? Okay. For 4, it says reactant A underwent a decomposition reaction. The concentration of A was measured periodically and recorded in the chart above. Based on the data, what is the rate law? All right. I immediately look at this and start doing crazy calculations in my head because I'm not used to seeing time and concentration. And not only that, but concentration of just one entity and not two different substances. What you should notice is that for each of those concentrations, it is halving. From 0 to 1 hour, it halves. From 1 to 2, it halves. From 2 to 3, it halves. This has the same half-life. A has the same half-life no matter the concentration of A. So immediately, based on that definition, I know that this is first order. And it is first order because only first order reactions have the same half-life regardless of concentration. That's where we get the formula T1 half equals 0.693 divided by K, because it does not matter the concentration of your substance. So I know that A is first order. So immediately I can write the rate law as K times the concentration of A. Okay, so if you see something with time and concentration and you start to panic, think half-life, because they're trying to trick you. It might not be as obvious as this one, right? It could be that it takes a little more time for it to halve, but in all likelihood, this is going to be a first order reaction. For 15, it says, which of the following graphs may have been created using data gathered from the reaction above? All right, so that is the rate for this reaction is second order. So remember, just as a review, and this is the explanation you should include if I ask you about it. If, when you are graphing the natural log versus time, you get a linear plot with a negative slope, then your reaction is first order. If, when you graph 1 over concentration versus time, you get a linear positive plot, then it is second order. So since this is second order, your answer for this would be D. So make sure you're comfortable explaining it as well. Finally, for 16, it says, after 44 minutes, a sample of potassium is found to have decayed to 25% of the original amount present. What is the half-life? So remember, the definition of half-life is the time it takes for half of a substance to decompose. So in this case, half hasn't decomposed. An entire 3/4 of it has decomposed because I only have 1/4 of it left. So not only have I halved once, I've halved that half again. So 2 half-lives have occurred. And let me show you that. So I go from 100 to 50%, then from 50 to 25%. So that is 2 half-lives. So if it took 44 minutes for 2 half-lives to happen, what that means is 1 half-life takes 22 minutes. And that's it.